Now we're going to go over some properties of the definite integral. Recall that the way we have defined the definite integral of a function over an interval AB is via Riemann sums of the function for a pointed partition, or in general for pointed partitions. So this Riemann sum is given by in each subinterval in the partition we have a sample point, we evaluate the function at this sample point, and we multiply that number by the width of the subinterval. We take the sum over all the subintervals of the partition, and that is a Riemann sum for f and the pointed partition. The integral, if it exists, is simply the limit of these Riemann sums as the parameter of the partition goes to 0, where this parameter is simply the maximal width of the subintervals. And integral from a to b of f of x dx is the notation that we have introduced for this integral. What we have seen previously is that the existence of this integral is guaranteed under the assumption that f is continuous on the interval, and that the geometric interpretation in the case of a positive function is that the integral is the area under the graph of the function. Now the first observation is that the integral from a to a of any function is 0. This comes from the fact that in the Riemann sum, if the interval for which we look for a pointed partition is reduced to a singleton, then the width of each subinterval is 0, and therefore the Riemann sum is going to be 0 because each one of the delta k's, xk's is 0. Similarly, if I integrate from a to b, I obtain the opposite of the number I would obtain integrating from b to a. The reason is that if instead of integrating from a to b, I integrate from b to a, that means for each delta xk I'm going to reverse the order and obtain the opposite of the length. And therefore I get the opposite of delta xk in each term in the sum, so a negative sign can be factored out, and then this remains passing to the limit. If we integrate a constant, c here is a constant, from a to b, we obtain this constant multiplied by the width of the interval, in other words b minus a. For the sake of argument, this is clear what it means geometrically in the case where, say, c is a positive constant and b is larger than a, then we have a picture of that sort. And then the integral is the area under the graph of the function, in other words this rectangle that has height c and width b minus a. The integral of a sum is the sum of the integrals, and this is relatively easy to see from the Riemann sums. If I consider the Riemann sum for a certain pointed partition of the interval AB for the function f plus g, then I'm evaluating f and g at the sample points, take the sum and multiply that by the width of the subinterval and take the sum over all the subintervals. Of course I can distribute inside the sigma sign, and I get the sum of f of xk star times delta xk plus g of xk star times delta xk. But since I have a finite sum of such term, I can write it as the sum of two Riemann sums. And then, because if the function f and the function g are both integrable, let's say continuous, then we have a limit for the Riemann sums for f over pointed partitions as the parameter of the partition goes to 0, and similarly we have a limit for the Riemann sums of g for pointed partitions as the parameter goes to 0. And so, because the limit of a sum is the sum of the limits as long as all the limits exist, we obtain that the integral of f plus g is the integral of f plus the integral of g. Something we have seen in the previous video is that the integral of x from a to b is simply b squared minus a squared over 2. If I integrate a constant multiple of a function, so a function of the form c times another function f, I can pull out the constant c out of the integral, and I get the constant multiplied by the integral. Again, this comes from the definition in terms of Riemann sum. If I consider a particular Riemann sum for a particular pointed partition, I have this common factor c in each term of the sum, so I can pull it out as a common factor, and I get c times the corresponding Riemann sum for f. Passing to the limits, we obtain the integral formula above. Another observation is that to integrate a function f from a to b, one thing that I could do is integrate from a to c, where c is another number, and then integrate from c to b and add these two integrals together. Now, to illustrate that, even though this is true whatever a, b, c are, for the sake of argument, I'm going to assume that f is a positive function, that a is less than c and c is less than b. Now, in that case, if I look at the integral on the left-hand side, from a to b, this is the area under the graph of the function over the interval ab. If c is between a and b, as I mentioned, then the integral from a to c is simply the area under the graph of the function over the interval ac, so this blue area, while the integral from c to b is the area under the graph of the function over the interval cb, so this green area. And now from this picture it should be clear that if you add together the blue area and the green area, you get the red area. Now with these properties, we can illustrate these properties on a few examples. Let's say we want to find the integral from 1 to 1 of the function x squared cosine x. Because we have seen that the integral from a certain number to the same number is always 0, we conclude that this integral from 1 to 1 of whatever function is going to be 0. In the second question, we're asked to find the integral from 9 to 4 of square root of t dt, knowing that the integral from 4 to 9 of square root of x dx is 38/3. We've seen that if we integrate from a to b, we get the opposite of what we obtain if we integrate from b to a. So in particular, the integral from 9 to 4 of square root of t dt is the opposite of the integral from 4 to 9 of square root of t dt. But now, in this latter integral, from 4 to 9 of root t dt, t is simply the name of the variable. I can call it t, I can call it x, I can call it Bob, it doesn't matter. So this is really the same integral as integral from 4 to 9 of square root of x dx, and what is given to us is that this integral is 38/3. So that means the integral from 9 to 4 of root t dt is negative 38/3. In the third case, we're looking for the integral from 0 to 1 of 5 minus 6x squared, knowing the integral of x squared on 0, 1 is 1/3, a fact that we have established at the very beginning of this module. We have seen that the integral of a sum of two functions is the sum of the integrals. Therefore, the integral of 5 minus 6x squared is the integral of 5 on 0, 1 plus the integral of the function negative 6x squared on 0, 1. We've seen that if you have a constant multiple of a function, you can pull out this constant. So that means I can rewrite this as the integral from 0 to 1 of 5 minus 6 times the integral from 0 to 1 of x squared. We know that the integral of a constant is simply this constant multiplied by the width of the interval. So I can obtain the integral of 5. It's going to be 5 multiplied by 1 minus 0, so just 5. And on the other end, the integral from 0 to 1 of x squared is given to us to be 1/3. So we obtain 5 minus 6/3, in other words, 3. Finally, given that the integral of a certain function from 1 to 5 is 12, and the integral of the same function from 4 to 5 is 3.6, we want to find the interval of that same function on the interval 1, 4. We've seen that to integrate from a to b, I can integrate from a to c, and then from c to b, and add these two integrals together. In particular, to integrate f from 1 to 5, I can integrate from 1 to 4, and then from 4 to 5, and add these two integrals together. Solving for the integral I'm looking for, the one from 1 to 4, I obtain that it's equal to the integral of the function from 1 to 5 minus the integral of the function from 4 to 5, and I have values for these two integrals, which I just plug in, 12 minus 3.6, and I get 8.4. Now if you turn to the next video, you're going to see more properties of definite integrals, in particular in terms of comparison and inequalities.